this scenario that we are going to show you right now can be implemented with the code we have right now. I mean, with the service design that we did right now and the same rules. But because we have changed some things in respect to the UI and the rule design, we don't want to have a video that will be deprecated in 4 months. Again, this process can also be replicated at release 0 installation, but we would like to see the more advanced way of designing a new service. So I would go to this predefined, let's say, pre-install OpenSlice portal, which is our staging environment. And I would like to sign in with the respective account. Okay. So as you can see here, we have some initial, let's say, service design, the generic catalog, for example. We have the MBB category, and we have this 5G connectivity and internet access. Before we order it, I would like you a bit to have an introduction of this service to showcase what it does. So maybe I can follow the same pattern with the presentations and open this presentation this time. So again, this is a complex NFV-based, again, service design and deployment, the 5G as a service scenario, and it's based on the developed branch of OpenSlice. So the setup of this demo would imply an installation of the latest, let's say, developed branch code. This is what it is. An instance of OSM, an instance of Kubernetes, and that's it. This service also needs a Kubernetes system because the NFV-based service, which is the 5G core, is CNF. So it, at the end of the day, it deploys on top of Kubernetes. OSM instructs Kubernetes to have the respective deployment. So the outcome of this demo would be to design a service bundle this time. So not a single service that will have only one related service, but a service, rather a service bundle that will have multiple services with dependencies among them. By dependencies, we mean that we would like the first service, for example, to be deployed first. And only after this service is active, then the second service will start, etc. So this is a kind of dependency. What we would also like to achieve is the design of the NFV-based services, but this time not with a simple, let's say, deployment, deployment IP rule, but more complicated rules, both for instantiation and post-deployment phase. Also, what we would like also to incorporate here is the HTTP-based service, both with customer-related characteristics. So we would expect that this service will perform an HTTP requests, taking some input from the user, and also some service-dependent characteristics that will come from the deployment services. So this service is just to showcase that OpenSlice is not, it cannot be used only for deploying over OSM, but it can use this OSM as it can use every programmable interface with simple HTTP or every interface that provides an API. So we can deploy things on top of OSM. We can deploy things on top of Kubernetes, for example. This is what the first release will do also. And also can leverage third-party APIs via HTTP so as to have a full service bundle deployed. And the final outcome, of course, after we design or actually go through the design of the service, is to order the design bundle for deployment and have the 5G connectivity that we desire. So the service design itself, as we had a spoiler previously, so the service will be named 5G connectivity and internet access, or 5G as a service. This service will accept user input this time. So the user will have, let's say, power over the service and can select whatever characteristics find suitable. So this service will comprise of 3 related services. So the first one would be Open5GS UPF. So this is a CNF-based NFV artifact. So it will deploy through OSM a UPF network function on top of Kubernetes. And then the second service would be the Open5GS core. So this is again a CNF-based NFV artifact that will deploy the respective Open5GS core, which will deploy the rest of the 5G network functions except the pre-deployed UPF. So this distinction actually came for us because we wanted to support also multi-UPF deployments to a single core. And the final service, as expected, will be a HTTP-based service, which will perform an HTTP request towards a radio management server that is in charge of managing the respective G-node Bs or radio nodes that we host in the University of Patras campus area. So someone can select a specific node to access the 5G system from. So let's go back to the UI and see step by step how this service is being actually designed. Again, we will not design it right now. We have designed in the past, but let's go step by step. So let's see the customer-facing specification that we've said is available to the customer. So as you can see, this service comprises of 3 services, as we have said, no need to repeat it. And as you can see right now, this overlay service does not have any characteristics that are not interesting for the user. So as you can see, there is a characteristic of 5G radio nodes, which is a list, let's say, of specific radio nodes that the user can select. As you can see, it is configurable characteristic. So it implies that the user can edit it during ordering. You will see how. And then we can have the values could be in user-friendly names. Also, these are the names that the user will see. And these are the respective value towards the programmable interfaces that is not seen to the user, but obvious to the user, but it is what the actual HTTP service will require. Other instantiation parameters are MCC, mobile country code, MNC, RAM profile, TAC, and that's about it. So these characteristics, I won't go over that, are typical characteristics for the 5G system. And it's out of the scope of this presentation also. And again, this parent service or this overlay service has 2 characteristics as placeholder for the location of the deployed services. So this overlay service would expect that this characteristic will be populated after the deployment of the UPF with the respective IP of the UPF. And after this happens, it will also deploy the core that will actually take the AMF location from this and proceed with the final service. Most probably, now I'm actually narrating, I see that this is a gap here. So maybe we can see it before going further. We can see it as a picture, let's say, or as a flow. So the user would order the 5G connectivity service with these respective parameters that we have just defined. The 5G connectivity service it will acquire an order ID, as we've seen in the previous, a unique order ID that cannot be known beforehand. So during instantiation time and prior to the instantiation of the first service, which will be the UPF, this order ID will be injected to this service. You will see now why. This service, as it goes for deployment, it will be delegated to OSM, and OSM respectively will delegate the deployment of the service, the UPF network function, to the respective Kubernetes. And here note that the namespace, the deployment namespace of the Kubernetes will match the order ID. So this way we can achieve isolation, which is only mapped to a specific user that orders the specific core. As the UPF will be deployed, then we can have the UPF IP address, and only then the rest of the core can be deployed, because the UPF IP address is a prerequisite for the rest of the core to be deployed. So the core will accept the second service, will accept some user-defined parameters, which is the MCC, MNC, and TAC, as you can see here, and also the UPF IP from the previous service. This will lead to a deployment of the core CNF and the respective services at the Kubernetes, again in the same namespace. This is the reason that the order ID is the same. And after we extract the AMF IP, which is the AMF IP is the one needed for the connection with the respective radio nodes, and we delegate this connectivity process to the final service of this deployment, which is the connect radio. So this takes as input the MFIP, which is extracted after the deployment of the service, and also the user-defined characteristics that was actually accompanying ordering of the service. So the connect radio, in respect, after activation of this service, it will forward an HTTP request to the radio management server, a specific HTTP request, which follows TMF resource API, but can be whatever API, of course, and as soon as it is programmable. And then this request will be delegated to a specific agent to the respective radio node that the user selected. So the radio management server will trigger the radio management agent of the specific G-node P and instruct the specific radio node to be connected to the deployed core. So this will finalize the 5G connectivity as a service. Okay, so having said that, let's go back to the UI now. And this is, as we've said, the overlay service. And let's go one by one to the services. So before actually we begin, let's see the first rule of this overlay service. This is a creation rule. Creation rule, as we've said, is a rule that actually blocks the creation of all the related services simultaneously, because as we've said, we wanted some service dependencies to be fulfilled before next service is being deployed. So for this, we will populate this rule, which runs continuously until all the services are deployed. We'll try to populate the UPF location placeholder, as you've seen, with the IP address that finds at the first service, which is the UPF deployment. So this overlay services oversees the first service and searches for the UPF IP characteristics. As soon as this is populated, then it will create the second service, which is the open 5GS core NS. And as you can see, this will be created if this sentence is true. So this will be created if the UPF location is not null. And also it can also pass some specific characteristics, instantiation characteristics to the 5G core service, as we have seen, which is the UPF location, MNC, MCC, and TAC. The same goes with the next service. So the placeholder for the AMF location will be populated only after the second service is active, and this characteristic is being populated as well. And the third service will be instantiated only if this placeholder is not null with the respective characteristics. So these are, in terms of rule design, the things you've seen graphically before in this presentation. So this is the creation rule that handles the dependencies among the services. Let's go to the services one by one. So the UPF service is the first service to be deployed. Again, the UPF have some specific characteristics. So I think this seems quite familiar because this is an NFV-based service. So it has to have this OSM configuration. As you can see, it's broader now because it's a more complex service than the previous one. Let's not go over it. This is automatically created anyway. And as you can see, we have the placeholder UPF IP. This needs to be populated after the deployment of the service. And this is what also will be leveraged by the overlay service to continue the deployment. So before we begin with this service, we've said that it needs to execute two things. Let me go back to the presentation. So this UPF service, before the deployment, needs to actually accept the order, the unique order ID, and also after activation needs to extract the UPF IP in a specific characteristic. So let's see it depicted as rules. So pre-provision rule, which this is a lengthy rule, but it can be easily comprehensible. So what it does is create a local variable with the original, let's say, OSM config characteristics, as you have seen. And what it does is it tries to populate the OSM configuration, which is what OSM will accept, with this new JSON. As you can see, this JSON is identical to the previous one, but some properties are marked as variables. So as you can see, instead of having hard-coded text here, we have variables which are populated in serial way with this variables array list. So we would expect that we will have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters, and then we have 9 placeholders for parameters. And the first, let's say, list item will actually populate the first parameter placeholder, etc., etc. What we're interested in is this specific placeholders for the current service order ID. So this is how we acquire the service order ID, which is something we cannot know beforehand because it is randomly assigned. So this will go to this Kate's namespace. So now you may understand how this namespace is being defined, and also at this service order placeholder. So let's proceed. Sorry about that. Graphical glitch. And also we have an after activation rule similar as the previous one. So we would like to have the UPF IP populated from the VNFR. And also, as you can see, the path is different here, because when we are talking about CNFs, the IP addresses are acquirable in a different way. So this is what have been asked previously. The service designer needs to know beforehand where to find the IP address, but since it is executed once, then it cannot change throughout the deployments. Okay, so this is the UPF service. Let's go a bit forward to the core. It will follow the same rule, the same OSM configuration. It will also have placeholders for other parameters, MCC, MNC, TAC, if you remember, and also the UPF location from the previous services. Again, the rules do the same job. The pre-provision rule will inject service order ID to the Kate's namespace parameter, along with the other parameters that we would like to populate for this service specifically, as you can see here. And in the same way, let's not waste time here. Let's go to the final. I would like to also show the after activation rule, which populates the respective AMF IP characteristic with, again, the VNFR of the deployment with different path this way. So this can be quite dynamic. So right now, we just know that there is an array, for example. We are interested in an array or in an object that has the name of AMF SSTP, as you can see, external IP, etc., etc. So this can be quite complex rule design if you want to parse something from a JSON object. And last but not least, so as to go for the deployment, we have the Connect Radio service. So Connect Radio service offers specific characteristics, and these are the characteristics that derives from the user. So this, and this are all user related. This is the characteristic that comes from the previous deployment of the service. And this is the special characteristic that notates that this service is not, let's say, orchestrated, or is not handled by orchestrator so as to track the state of the service or bring it to active by following an orchestrator, but it is rather automated service that will come to active as soon as the HTTP request is being executed. If we don't have this characteristic, then we will have to manually activate the service to execute the HTTP request. These are, I mean, the choice, every choice that someone would need to have. And to finish this, the last rule is the most lengthy one, is the HTTP request. So before we construct the HTTP request, we would like to have a local variable. This is a quite technology specific, so it doesn't affect, let's say, someone on the deployment. So this is the GTP addresses of the internal GTP addresses of the Gnode Bs in place. So we just check that if specific radio nodes from the user is being selected, then the GTP address is altered. Okay. The same goes with NSSI, which is another property that is requested by the radio management server, and this is where the payload of the request is being structured. As promised, the payload is this one, and it follows the TMF resource model, and it will prompt the specific Gnode B for an action, which is restart, and also for some action parameters enforcement, which is these parameters here, that will derive from the user input, such as tag, PLMN, indirectly GTP address, and TDD, which is the RAM profile, and also the deployment parameters from the previous service, which is the AMF address. So as you can see, the first parameter, it's AMF. The second is the local variable, same to the second. PLMN is a combination of MCC and MNC. So this combines these two user-defined characteristics, tag and profile. So this is the payload. The following variable is the URL that someone will find this radio management server. Of course, there need to be connectivity between this instance of OpenSlice and the radio management server, but this is not part of the OpenSlice itself. It can be quite, let's say, infrastructure specific. And then this is the variable that actually executes the HTTP request, which is a path, as you can see, with specific headers to a specific URL with a specific payload. So this is the URL and this is the payload. And for debugging purposes, we have selected to also expose this as characteristics. So the user, when this happens, will see the request sent to the radio management server, and also the response if everything goes as planned. So enough with this, let's go straight to the deployment. And this is what we did in the past. So this is the markdown support. So you can have images, you can have whatever you would like for display purposes. And also right now I will order it. Let's assume I'm a simple user. So these are the, let's say, predefined values. Let's keep them like this. I mean, I can change, for example, I don't know, the tag and tag, maybe. Okay, just to have some diversity. And I can proceed with ordering of the service, again, for 1 day, for example. What to expect here is for an administrator to come and review the service. So you can see a calendar of service orders. As you can see, this is more usable OpenSlice instance, so it has more calendars, more services ordered. And as we expect, this administrator would change the state of the service to acknowledged. And from now on, everything is on hands of the respective orchestrators. OpenSlice internal orchestrator, which is awesome, and underlying orchestrator, which is OSM and respectively Kubernetes for the two first services, and the radio management server, which is the third service, so as for the Gnode B to be connected. So the deployment started, as you can see. The service is in progress, and as promised, as you can see, this is the overlay service that have started, 5G connectivity and internet access. Not every service started simultaneously. So we would expect, as again described, the UPF service to be deployed first. So this is what's happening right now. We can go back to this graph. Let me just go to this. So this is what's happening right now. And this is delegated to OSM specifically, and also to the Kubernetes. So let's check this. Let's look into the OSM. As you can see the service order with this unique ID. This is where this pre-provision rule injected this unique ID. As you can see, this is the service order, and this matches the service order, of course. And this, as promised, we would expect to be the namespace that UPF is being deployed upon at the Kubernetes. So let me open this tool, the lens that monitors the cluster in interest. And let's go to the, let's say, services. And as we can see, we can have a UPF deployment. Let me actually come down to the specific namespace, F5. Okay. So as you can see, we have the UPF deployed in this cluster. This is active, as Kubernetes says. It has been assigned an external IP of 0.222. So this is what we expect to see on top of OpenSlice. Let's see. So OSM says that this service is deployed, as it seems. And let me go to this. When this happens, as you can see here, we would expect that this active service will be also reflected to OpenSlice UI and also to the user. And the UPF IP will be forwarded to the next service. So let's go back to the OpenSlice UI and check. As you can see, actually, this goes a bit faster than expected. As you can see, the first service is active. Okay. The UPF IP is here. And as expected, it is also reflected at the overlay service placeholder, right? So this was the prompt for the next service to be instantiated. When the next service is also complete, we will have also a value here. So let's go to the next service, which is the Open5GS core. So we'll expect this characteristic to be populated eventually when the service is active. And as we can see, there is the MCC, the TAC 999 that we have defined, and UPF location from the previous service towards the core. Okay. Again, what we expect to see, because it follows again. It follows again the same logic. The core will be deployed on OSM and also be reflected towards the Kubernetes in the same namespace. Let's see what's happening. This will be it. OSM. And if I refresh now, I can see the core already deployed. Nice. And this is the core. So let's check also the Kubernetes. And as we can see, the core is also there, the full core now, with the external IP of 0.224. Okay. And this should be reflected also at the UI of OpenSlice here, as you can see. So this service is active. We expect that it will expose the final IP address. So if we refresh it again, most probably we'll see it right now, as promised. And this is also reflected to the overlay services. And as you can see, we haven't time actually to check it because it happened in parallel. we have seen the last service also deployed, which is the integration of the radio node. So what you can see here on the overlay services is that the AMF location is populated, okay? And this is the trigger for the final and last service to be deployed. And as you can see here, again, this is the service that actually was triggered. It receives the the 5G radio node, which is a specific node here. It receives also a specific AMF IP, specific MNC, RAM profile, and tag. And if we refresh, most probably we will also see the specific requests as promised. So as you can see, this is a request towards the radio management server, taking the parameters that we would expect. So the AMF address is the one that we have seen prior, and it matches perfectly the AMF address that we can see here. Okay. And we have seen the Kubernetes as well. This is something internal, as we've discussed, same as this. And these are the parameters that the user actually defined. So this is the MCC and MNC. This is the tag 999. And this is the integer representation of the RAM profile of low latency. And this is the response from the radio management server. And that would be it. That conducted actually the 5G as a service demo. And what we have, no, this is not the presentation. This is it. What we have right now and showcased is this scenario over here. So I think we are just on time. Let me tear down the service so as to see the tear down as well. As you can see now, this is service. If we leave it as is, it will tear down automatically tomorrow. But if we prompt it to terminate right now, in the next 1 or 2 minutes, we will see it coming down and also disappearing both from Kubernetes and OSM. So that would be it regarding this demo. Hopefully, this is the demo that we were trying to build towards. I think this is the most interesting one. And if someone still needs to answer some questions and have the time to stay a bit more, we are more than willing to accept any questions.